Big data and artificial intelligence, that's something that is creeping into our life in a way, because you know that we have so many applications of artificial intelligence that makes our life easier, like smart home, for instance.
Playing jazz.
Smoothie.
So it's very convenient. You just say a few things and things happen.
Meetings today. Remember, dentist at 9:30.
Fire off.
Fire off.
You don't have to look much and care much.
Open.
Everything happens like magic.
We're going to do one more.
Oh, yeah.
But then there is this moment
Wrong voice command.
when things go wrong.
Wrong voice command.
Open door.
Repeat that.
Open door.
I didn't understand that.
Hey, open door.
Play on the floor.
Get on the floor. Open the door. Open the door.
So it really shows that there is a very small balance between the data learning set that provides enough information and that provides too few information to cope with situations that are not being foreseen. And I think this is one of the facts that Andreas Dengel will allude to and will be able to explain how important it is for machine learning to keep this balance. What do you think, Ivan?
I completely agree with you, as local anesthesia was a big game changer in medicine and in dental field. You showed us how some of the everyday applications of AI, such as voice recognition or things that we use, can draw us to some, let's say, not really great conclusions. But that's why we have designed a really interesting session that might tackle and reveal important information in the era of digital data and digital transformation. That's why our great honor is to have today with us Professor Dengel. Andreas Dengel is professor at Technical University of Kaiserslautern. He's also executive director of German Research Center, an impressive institution for artificial intelligence. In his really interesting and tremendous career, he has also been awarded a professor from 2009 at Osaka Metropolitan University. He has been awarded many scientific awards, one of them being elected in 2019 as one of the most influential scientists in the history of AI in Germany. He has also received an Order of Merit by German Ministry of Science and Education. An interesting fact is that he is one of the very few scientists receiving an award of the oldest Japanese order, called the Order of the Rising Sun with neck ribbon and golden rays, awarded by His Majesty of Japanese Emperor Naruhito in 2021. With all of this said, I'm leaving the stage, and please give a warm welcome to Professor Andreas Dengel.
Yeah, thank you very much for this really kind introduction. I'm glad to be here. It's an amazing audience to see you all. I never had such a big audience. And so I'm talking about, of course, AI as an AI guy, but I'm not giving you a seminar, and I will not answer you all the questions you might have regarding this dynamic development, but rather give you some insights into the potential of AI. About different aspects. Henning asked me to be more abstract. We also have a system for fake implant recognition, but I'm giving you more insights into other things. Still waiting for my slides. What should I do? Should I take this and then click? Okay. So I'm the first, that always happens. Aha. Here we are. So, very good. So I'm talking, of course, about data because this is a quite important aspect. If you don't have the data, we cannot manage anything. But first of all, I also give you something about good data, some aspects and the deep insights into, well, the data aspects, the features in the data, and of course some ideas of how to understand the behavior of artificial intelligence. But first of all, I ask you, who knows DFKI? Could I see your hand raised? Ooh, that's quite poor. We are the largest independent AI research organization in the world, with a headquarters in Kaiserslautern, more than 1,500 employees. And we have, as a company, we are a research company, many shareholders, also not only including German ones, but also the big names from US like Microsoft or Google, Intel, NVIDIA, and others. But as an independent institutions, all of them have the same share. And we are running more than 500 projects at the same time in all parts you can imagine where AI plays an important role. But that's just for the introduction, and I'd like to start with a typical pipeline you might know from different other applications that is pre-given in many settings, not only in medicine, but here we are building on data from various sources. This could be experimental data, this could be biological data, this could be environmental data, also measured data via sensors where you wear some devices. Specifically, also you have clinical studies where the data comes from. And if you have a data, the traditional way is that you do something like feature engineering, that you use biomarkers or your background knowledge and you identify this is important and that's minor important and so on. And based on that, you have the task to select the right methods to be applied on these features. And of course, neural networks play an important role here to do regression, clustering, classification, etc. And at the end, you have this model which you could evaluate by given settings, and then you do a kind of re-evaluation. The good news is, after many years of this feature engineering, we don't use it anymore, we don't need it anymore, because we have now machines which learn end-to-end, namely deep neural networks, where you can just train the system using data in order to find out the features itself. Yeah, some systems nowadays have maybe billions of features which they extract, much more than our complexity border is able to handle somehow. And they are running in a way that they usually outperform all traditional methods if you have the data. Not only the big data, which I can show you. And a typical example in this domain is, for example, an end-to-end approach which is detecting the early stage of diabetic retinopathy. A typical problem in medicine where you are lacking in features and you are lacking in data, because the features themselves, so the biomarkers, are distributed all over the images, and in early phases it's quite hard to recognize them. And the same holds also for the data. And so the traditional methods which are usually used for images like convolutional neural networks, CNNs, they have trouble in doing that. So, but the good news is that AI has a kind of evolutionary time, that in the last 10 years many promising approaches occurred. And here there is a kind of ensemble technique where you use two networks. One of them is using is solving the task of feature localization, and then after having the features, you can classify the features according to the degree of a disease. And therefore, it's not necessary to have this huge amount of data already. Everything is published, and you can also read through this publication the accuracy of such a system. All right, so today I'd like to talk about the role of data, which is quite important. And the data itself plays a role in many aspects. And if you look at the human body, there are lots of different levels of information which is given. There are plenty of cells, 30 trillion in total, of different type. The cells themselves are composed of different nucleus, with 23 pairs of chromosomes, and the chromosomes themselves also have 100 to thousands of components, nucleosomes, which then, of course, have DNA, RNA, proteins, etc., etc. So we have genes and non-coded aspects here, and plenty of dimensions to investigate, even with the premise that each body is individual. So if you look into this, there is one, for example, field. This is about cell analysis. And if you have a probe of cells, you have this Petri glass, and you could put in the probe, and then is the challenge how to do your experiments. And one typical way in the past is this fluorescence, which is used to study the cellular behavior and the processes inside, but it's quite expensive and time-consuming. So, and of course, this invasive labeling technique is given, but also you have only shorter periods for the investigation. This is a disadvantage. So it's better maybe to use these label-free images, which are cheap. You can quickly take them. You have a longer period of time of examination. However, these label-free images, which are investigated by contrast microscopes, they reveal some challenges, and that's what we found out. If you look at the public available data sources, they are quite low in contrast, and they are irregular by the cells which are shown in the images. We have unclear boundaries. The cells are overlapping. They are quite small. Sometimes they have a high density. Sometimes they are rare. And so it's quite hard to apply AI technology on this type of data. And if you look at the data sets, even at the most promising one, for example, the Avican data set, it has at least some thousands of images for 30 different cell types and multiple microscopes in case, but there is still a poor image quality, so blurred images are part of this. We have only partial annotations, so even there are many cells inside the image, only some of them are labeled what type of cells they are, and at the end we have only a small number of cells in average for each image. So it's not sufficient to really do an analysis here with AI. In this way, we work together with some scientists of Sartorius, where we generate also with generative technology some artificial images, but also provided at the end a mix-up of fully annotated images here, where we have about 1.6 million cells inside, 313 cells per image, with the 8 different cell cultures at the same time. It's also published in Nature, and you can see what happens, that we have about the same distribution of all the cells. And the good thing is, if you have such a data, you can automate some tasks, like the one shown here, where you have a kind of video, or say every 5 minutes, where you have a picture about a cell culture. And those who are aware of this topic, they know that in the past you had this manual labeling of the cells in each image to see how cells behave. But with such a data set, you can train a system so that you have an entire pipeline with the automatic tracking of each cell, and even the cell splitting is recognized and new numbers are given, which is easifying the way. And this is also now part of the products which are online, so the new microscopic generation has such technology as services inside. This is some example how important data is. A second example I want to address is explainability, which is for artificial intelligence a quite important field, because you usually have data, and then you take or select a certain topology of a deep neural network, and then you show the system the example of the data, and at the end, like in autonomous driving, the system behaves somehow, but we expect that it runs very well. And for critical dimensions, like in medicine, of course, you cannot just use a system that it makes automatic decisions for you, but maybe a second opinion, but at least the system should justify its proposal or decision-making at the end. So I'm taking this example because it's a very typical example in medicine where some colleagues at Stanford University already proved 7 years ago that you can get a quality of classification which is human-like. So distribute different types of lesions on the skin, melanoma, basaliomas, but also nevus, all the classes in some way. But the problem is that the system is a black box. It behaves somehow, and you don't know what happens. And it would be very nice if the system, as I told you, is able to explain decision-making. And I'll give you an idea how this could work. So in these skin lesions, you have a couple of structural features of these lesions here. You have regression structures. You have some complex lesions which are quite colorful. You also have extensions, radial extensions in various dimensions. Also the boundary is somehow different. You have a network, typical pigmentation inside. And this is also something where the specialists in practice work on. They have some, of course, also devices to take pictures, and then they look at the pictures which are large in size. But in many cases, they also use some help. One is, for example, this ABCDE rule, where they have checklists to look at the different lesion individuals and then have these concepts, this dermatoscopic criteria ranking, how present a certain visual concept is in. So what happens is that the system is going to, at the end, to score the opinion of the expert and gives a certain score how suspect a certain lesion is. And this approach could also be transferred to an AI system, but again, we have no gold standard here. You can't find these large databases which are necessary to get a great result by AI. So you have to think about a tricky way to do it. So what we did here is we had a 3-step approach, namely to have at first an idea to establish a high-quality image classification network which is using a very large data set. And in the second step, you're going to train the visual concepts of your domain, here the skin lesions, so you have to think about how to do it. And in the third step, you adapt the network through transfer learning to the skin lesions. This sounds abstract, but what we do here at the end to reach such an explainable AI system is we use a big data set about images on different types of animals. And we train the system on these pictures to get at the end a high accuracy to classify what's inside the pictures. And the network was explicitly trained, was not trained on lesions, but on something different. So now, oh sorry, there is something misspelling here in the pictures. In the picture, it should mean pre-trained CNN here. So in the second step, as I told you, we have this medium-sized database, but we have no adequate data set of skin lesions. So what we did is we had make use of a textile data set, where we have textiles which show different patterns, dots, stripes, and so on, which are also typical, somehow present in different form in the pictures we get from the lesions from skin. And at the end, of course, for the trained network now, the system would come out with zebra and tiger, which is definitely wrong. So to adapt the network to the new visual concepts, we take a feature of deep neural network, namely that if you train the system close to the input data, they learn very elementary features of pictures, namely edges and corners. And the closer you go to the output, the more complex the features become. Like in face recognition, at the end, close to the output, you have entire faces. And based on that the network is stepwise learning features elementary to more complex one, we are taking this idea, the characteristic, and then tap our network at certain stages to take the features out and to train concept classifiers like striped and dotted. And in the third step now, we use our data set of skin lesions and adapt it in a way that at the end there is a system which is able not only to classify on the left-hand side whether it's a nevus or something else, but rather also to show you how present the concepts are in the picture and then transform this presence also in a textual statement, which you can see over there. So the system is now in a situation to act as a second opinion for the specialists. And moreover, you could also use some tools like heat maps, where you can use a slider to see how the presence of certain concepts in these images are. And this could also be transferred to the bit more challenging, of course, task to consider lesions in your mouth. Anyway, last but not least, you know about the data importance now, and for researchers as well, for practitioners and experts, we need access to the data and the exchange of data. And you now might be heard about the European Health Data Space, which is established to enabling this sharing and also to include aspects of data privacy, security, and also ethical things. There are a couple of dimensions like data accessibility, interoperability, data security and privacy, and further also doing research on somehow anonymized or aggregated data in a certain sense. However, there are many question markers still to share the data in an adequate way. Not only it is not that easy to say what is AI, is a system already AI or not? It's not that easy, because AI is not just deep learning. There are many tools available, but there are many open questions which are important to address, because the committee is composed, of course, of different disciplines, and the understanding of this amazing and evolutionary technology is hard. So, to sum up and give you some takeaway for this short talk, AI is nothing to replace humans. It's an extraordinary tool which you can use, in our case, as a second opinion and an assistant, but it can reduce complexity if we are overwhelmed with data. So consider it as an intelligence amplifier, which helps you to get a faster insight or to push up your task. And at the end, it could help us to also detect new things, to prevent different aspects at the same time. So thank you very much for your attention and time. That's it.
Thank you, Andreas Dengel. Before we move on, and before I ask Henning Schliephake to introduce our next speaker, after the next two expert speakers, we will also have an interactive discussion with you, and our next speaker will also want to know something from you. So I would like you to take out your phones and have them ready. Make sure they're in silent mode. And if you haven't done so, make sure you're able to surf to the Mobile Congress website. You find it in your mobile web browser, and you surf to app.eao.org. We might have a QR code up, and otherwise it comes soon. There it is. You can also just scan the code. You enter our Mobile Congress app, and in the homepage, in the red, you see a small box that says Interactivity. When you click Interactivity, you go to room Berlin. That's where we are today. And as soon as our next speaker has a poll open for you, you'll see it here. And also, if you have any questions, you can submit them via this Interactivity box. Henning.
Thank you, Gerrit. Well, thanks, Andreas, for having this wonderful lecture that sets the stage in a way how complex artificial intelligence is and how much data you have to come to reasonable conclusions. Tim Joda is our next speaker. Tim Joda is head of e-health in reconstructive dentistry at the Clinic of Reconstructive Dentistry in Zurich, so at Ronnie's department. He is triple board certified as Prosto, as perio, and in implantology, so he has strong roots in clinical service and clinical treatment. He is a Master of Science in
Artificial intelligence, one of the buzzwords, the topics right here, and I'd like to focus on these 4 things: diagnostics, visualization, maybe a little bit less about patient communication, but also on robotics, big data, the next speaker focusing on that topic, and of course 3D printing, and more in a social context, sustainability in general. And don't forget about the thing, we are very privileged and we have access to a lot of other things, but not all of the people in the world have access to this great dental care. And maybe AI will be a tool in the future that we can use to create better care for all of our patients. Just to have in mind why it is important, maybe, AI from an economic perspective in the health market, in the global health market in general, and then we can see there is a lot of things going on in robot-assisted surgery and in clinical trials. And as I said, economics, it's very important and the driver nowadays for the industries to proceed. This is a value on the last year in 22 of more than $15 billion US. And it's predicted a compound annual growth rate of almost 40% in the next years. So there is a huge market that we see, maybe not only in dentistry, we are always lagging a little bit behind than in general medicine, but this is a big, big topic in healthcare. But how will AI change implant dentistry in the next years? So here I'd like to focus on the classic implant workflow in the digital age, starting maybe roughly with the data acquisition, treatment planning, implant surgery, the digital impression to capture this 3D positioning of the implant, implant prosthetics, and patient monitoring. I cannot address all of these topics, so I have chosen 4 of them, and I now want to highlight in these areas. First, with the treatment planning from the beginning. There is a lot of AI tools having for 2-dimensional X-rays, for periapical panoramics. For instance, in the terms of redentistry, nowadays it is important to have a tool where automatic identification of an implant will be provided to us as a clinician. But here, now I want to focus on the cone beam CT and the 3D planning in these terms. So first of all, of course, we have to diagnose our radiological data. And here we have a lot of tools and help from the AI. As Andreas said, it's a supplementary tool. It's not a replacement of the human to identify teeth, implants, to automatically create a dental record. Skeletal landmarks, maybe pathologies will be identified in a better way. Such an algorithm will not get tired, will not get bored like a human, and therefore we have it for 24/7 access to such an tool. And of course the analysis for the TMJ and airways. Why showing airways? This is maybe for the Braxa and for apnoe. This will be very important in the future there that we have analysis of this as well. Moving on now, creating an implant treatment plan. Then we know we have to merge the DICOM data with the STL file. We have to identify the alveolaris inferior in case of a mandibular case. And of course, we need to segment to prepare all this data in advance. This can be done by a human, but of course, we have already commercially available AI assistants who can provide us with this data set preparation, as we can see here at the example of the co-diagnostic software. Later on, of course, we have to analyze our prospective implant site. And here it's a nicely study, and that is shown that if it's defined for this single tooth spacement or in a 3-unit spans, that we can automatically analyze the width and the height in a horizontal vertical way of this bone, like the slices that are already provided by the cone beam CT. But this is now an automatically approach that helps us. It makes our clinical life for the treatment planning easier. In the same way for the soft tissue and to combine it together. So the logical consequence might be now, it should be there that we have an AI algorithm for the implant abutment selection. What kind of implant type that is already available, like a soft tissue level type, a bone level type, or even the material, would be the best choice for our patient in this specific situation, or even the three-dimensional positioning and the diameter. But so far, best to my knowledge, we do not have such an AI algorithm. We wanted to work on it, but we had to realize it is really hard to have enough structured, labeled data in advance to work on this project. I just want to emphasize another step, and we discussed this in a previous consensus conference already, that we have with the digital tools in advance for this treatment planning, also from a prosthetically oriented way, placing an implant and planning an implant, pre-surgically plan already the abutment. And this is really important, especially dealing on bone level type implants. So now, as Gerrit already mentioned in advance, I'd like to ask you, and it's just a simple question, it's just a no-brainer maybe, but what do you think? Who wins the battle of virtual implant planning? Not today maybe, but even in 2 or 3 years. Will it be the human dentist or an AI algorithm? I move on now, and let's move to the implant surgery. So maybe some of you think, oh, now we can see blood, implant surgery. This is why we are here. And these are the 2 topics I'd like to focus on. It is static and dynamic computer-assisted implant surgery. And maybe you ask yourself, okay, now we have an AI assistant in advance to prepare the data set. Is it so helpful? I don't know. But here now, it's a case where we can use the AI tool to have a better predictable outcome of our treatment. So here, the tooth is already inside, and I say it's AI-guided immediacy, so we can virtually extract in advance the tooth. It is superimposed with the STL file. We have the emergence profile. It's not changed anything. We do not have to damage anything just to calculate it. We have the best possible way to select an implant type with the high prediction that we can achieve there a primary stability. So the shape of the implant, the length, the diameter, and here in the superimposition, you can see the red area. Of course, this is the implant, and this might be the region where we have primary bone contact, and therefore we hope that we have primary stability. In blue colored here, we can automatically calculate now what is the amount of bone that is missing. So we have everything that we can discuss with our colleagues and with the patient in advance. This is now a case that were treated in combination with static guided surgery, as you can see here. Personally, I'm not a fan to leave any dental or tooth-related remnants inside, so we just used it, but as a pilot drill, as you can see on the left corner. But later on, because we did the AI-driven treatment planning, I already knew that we will destroy or remove all of the tooth remnants by the further drilling sequence. And then it's easy to proceed. We had primary stability, intraoral scanning, and 1 hour later we could provide these final restoration. So there it helps in these immediate cases. The next step beyond static guided implant surgery will be dynamic computer assisted implant surgery, with the real feel like a haptic navigation. We have in the University of Zurich 3 of these systems, and trying and playing at this time a little bit, and with Mark Balmer, one of my colleagues, and we are there in close collaboration. And this is one of the latest cases we did, and this is something really fancy. You have a freehand touch, you have all the flexibility, and you feel a little bit, let me say, like Superman. You can see through and see at the 3-dimensional X-ray the planning, and you have the freedom to change everything if you want to. And this is really a game changer for specific indications, let's say. And this is now the case that we did with Mark together, and this is the start of an ongoing case series we had here. I think now the technical development opened up new strategies, and you can see the tracer, the tracking, it's inside the mouth, and as you saw at the previous slide, it is not a huge technical environment that is necessary. It is the projection, the lighting, it's already integrated in the handpiece. So it's kind of handy, this situation, and you have the full flexibility to react to this. And then, of course, this is still at the beginning. And honestly, if you perform such of these surgeries with these dynamic navigation, it feels a kind of weird. So you have your arm here, the patient is there, but you look at this monitor, and then you drill a hole in the jaw of the patient. And nowadays, a lot of companies working, having smart glasses, mixed reality, to put it together, and then you can have the eye on the patient, and you can see it like a projection that you see otherwise on the monitor in your glasses, and then to perform the surgery. And I think this will bring this entire procedure a step forward. But then, of course, the next step already will be robotic-assisted implant surgery. As an example, and it was announced already last year in May at the NYU, first dental student-led robot-assisted dental implant surgery. It's not far away, it's reality in some of the countries and as well in China. And therefore, I'd like to ask you a second question.
We haven't seen the results of the first question. Aren't you curious to know and find out? Because that's how the system works. We can move on to the next one.
Okay.
So let's first look at the results
then
of question one.
Let's see, yes.
I think we can pull them up. The results screen of question who will play. Oh, we moved on to question 2. So apparently they followed you moving on.
Maybe
to question
we
2,
can
so
include this in the discussion.
Exactly. I'll bring it back to you. Okay.
So I thought this would be the way. So then the second question. So who will place more implants in 10 years? Will it be a robot guided by AI or a human dentist? I give you just a few seconds. It's not a brain worker, huh? Maybe you can help me to switch on the slides again, please. Now we see immediately the results. So it's still, but at least 1/5, 20% says that it will be an AI robot. So I didn't assume that, honestly. So let's move on with the presentation, please. What is the evidence using a robotic-assisted implant surgery system? And there is not much evidence out here right now. I found this case series involving 38 implants in edentulous cases. 2 of these patients were fully edentulous, and they were using this type of haptic navigation system. And here are the results of these 5 patients, not comparable, different indications maybe, full arch and both arches, just in the lower. But you all know these comparisons about the planned implant positioning and the real placed implant positioning. And here we have the numbers for the 3D apical deviation, angular deviation, and 3D coronal deviation. And if you look at the mean, then you say, oh, maybe not too bad, but I'm interested in the minimum and maximum because this is the highest risk I will give to my patient. And especially if you have a look at the 3D apical deviation, it is more than 4 millimeters in the worst case. And I think this is like a kilometer on the street if we are wrong way placing an implant 4 millimeters in the mouth. So there is still a lot of work to improve such a kind of system. But if we have just to sum up a little bit this, with the 2D, we have the possibility to go freehand for sure. With the 3D, we can combine everything. So this is maybe, I know, especially in Germany, there's always the question about, do we need a cone beam CT? But this, in the treatment planning in advance, opens up further steps using AI and digital technologies for sure. And I don't know if you're aware of this one. And this was announced, I think, in May this year. Tesla, the robot, and the development is so fast. It learns. There's a recognition. It's automatically they can move and walk, and they find every way back where they were. And this is maybe something for you, Henning, to scale up your business. You sit next time in your desk wearing the clothes and the goggles, and then placing an implant via a robot somewhere else in China or in Brazil or in Argentina. We are not right there at this time, but this will come in a few years. Let's move to implant prosthetics, and this is a short part, and I want to focus on two aspects, and we are working there with the group in Michigan together to have an AI algorithm for anatomical landmark identification for automatic maxillomandibular registration. It is still at the beginning, but this is very nice to start in a digital environment for our patients in full arch rehabilitation, in complex cases where we already have a cone beam CT. And of course, the virtual dental patient, we started with that 10 years ago. The treatment outcome simulation nowadays, the systems commercially available are there that we can combine an STL file from an intraoral scan, an OBG file facial scan, and a cone beam CT from DICOM data to put it together, and now having the movements, the 4D insight for the simulation. Just think about if we have to rehabilitate a maxilla and we want to discuss if it's a fixed solution, a removable, do we need the lip support, and so on. So there are still ongoing projects. Finally, I'd like to come to my last topic, patient monitoring and personalized implant care. This might be something new for you. And Henning already mentioned previously the topic of peri-implantitis. But I think the best treatment is to avoid peri-implantitis, and it's to focus on prevention. And here, our task at the University of Zurich is we want to work on biosensors, placing in the mouth of the patients to monitor saliva and to see if there are some markers and to maintain implant health. So we want to avoid to have an peri-implant inflammation. In this context, of course, the overall goal for us should be an AI predictive modeling to have like an avatar, a digital twin in terms of 4P dentistry. So that means the 4P that was already introduced by Dr. Leroy Hood, maybe I think 10, 12 years ago in the US. And this comes from this part personalized, so that we have a tailored medicine, that we have to be predictive. So starting in advance, what is the best way that we are involving our patients' participation, and in the end preventive. So this is something we are working, that we have a treatment simulation considering the individual risk profiles for our patient. In this context, let's move on to a last study I'd like to show you. This is a Chinese group, and they said, okay, we have a lot of data, retrospective data, and almost 700 implants included, and they showed who has lost an implant. And there were included 310 implants in almost 280 patients with a high risk because they lost the implant within the 5 years, and the other ones were the low risk because they was inside the implant. We do not know if it's a healthy or not, it's just yes or no, survival or not. And then they created a deep learning model, as Andreas has shown us, based on the clinical features, as you can see here, and the implant features. And then this is the task. Such a model will be developed based on an original data set, some percentage, some data will be taken from this, and then it's a training phase, and then you have the deep learning model, and then you have the test phase with the other percentage, in this case 20% of the data set, to train this model and to see what comes up. And these are the results. So here you see a predictive efficiency of 0.9. What does it mean? Nobody knows that. So this is a different language, at least for me. They say it's the area under the curve, as you can see there. If you translate it in terms of, let's say, 90%, and you say, oh, maybe this is great. But if you have a closer look at the estimated Kaplan-Meier curves, then you can see the actual, because it's a retrospective study, the actual lines and the curves, and for the low and the high risk, and the predicted ones. And then you can immediately see the prediction of the AI algorithm makes it worse for the patient, for the low risk, but it makes better for the high risk. So there, it's a lot of work to see, and I think maybe we have time later on to discuss this. What kind of consequences do we have? I'd like to come to an end, to my conclusions, and of course nowadays in the clinical work we are using a lot of digital tools and applications and data, from the acquisition to the oral rehabilitation, having inside a lot of material science, but nowadays we have to see and be aware of cloud technology, virtual patient simulation, augmented reality, AI, and advanced robotics. And as a take-home message, I'd like to sum up for you that what I emphasized with these 4 bullets in this digital workflow. I see a big potential for AI in imaging data collection and diagnostics in general, the automatic virtual implant planning, for the entire dynamic navigation, including robotics in the future, and the high potential for remote monitoring for implant health. And this is still a question we cannot answer right now, because it's just the machine, and in the end, we are treating humans, and they maybe want to be treated by a human as well. And I'd like to end up with a quote of this guy, Bill Gates, and he said, "We always overestimate the next 2 years, but underestimate the upcoming 10. And with that, I thank you for your kind attention.
Thank you, Tim Joda. Thank you. And Tim, for those who are curious, the answer to your first question was a very close tie. Who wins the battle of virtual implant planning? We have a 50-50 room, which with a 51.3% in favor of the AI intelligence. Close call.
And yeah, I just can say we have some preliminary results in the University of Zurich, and we can see it is definitely faster and more predictable with the AI tools so far. At least for the preparation of the data set.
Thank you, and thank you for participating in this interactivity bit. I also see some first questions coming in, so those will also be fed into the discussion with our speakers.
We'll have time for that, hopefully, in the discussion, and I would like to thank Tim for amazing lecture and opening up these really important questions, and I really hope that in the next 10 years we will have answers to all of them. I would like now to present to you our third speaker. Arjan Vissink is professor at the Department of Oral Pathology and Oral and Maxillofacial Surgery at the Medical University in Groningen, Netherlands. Professor Vissink is responsible for the research ongoing in this institution and with many ongoing projects in the above-mentioned fields. In his fruitful scientific career, he has published many international scientific papers. He has edited 18 books, written several book chapters, and participated in many scientific projects, also being awarded numerous scientific awards. From 1996 to 2006, he has been editor-in-chief of Dutch Dental Journal, and from 2016, he has served as an editor-in-chief of Journal of Oral Diseases and European Journal, International Oral Science Journal. Last but not least, Professor Vissink is conducting and is going to present a 9-year follow-up study on big data. So we are about to learn what big data is and what we can do and how we can work with big data. So please give a warm welcome to Professor Arjan Vissink.
Thank you very much for this very nice introduction. And also thank you to invite me to this nice conference. Big data in implant dentistry. Yes, refer to the words. In fact, big data in dental research and oral medicine is quite a lot, but in fact, there's not much big data in implant dentistry. It's just at the infancy. There's just a few studies on machine learning and artificial intelligence that was already discussed by Professor Dengel and Professor Joda. There are just a few studies about what implant performs best, who should place the implants, and a couple of more studies about the patients themselves. The first study, what do the sales data tell us about implant survival? That was a retrospective study about sales data of about 97,000 implants placed over a 7 years period. And what was recorded was just implant type, implant diameter, and implant length. And the results were not really surprising. The implant loss was about 2.78%. Most implants were lost early, like we know, and very few implants were lost after that period. And the shorter implants, and the implants were not very short in the study, it was just starting with 9 millimeters, had a higher early return rates. The 3.8 to 5 millimeter implants had the lowest return rates, and the 4.3 millimeters were the lowest. And when you make the diameter too big, the 6 millimeter had a significant higher return rate. But actually, this study does not learn us anything about the implant type or brand, the implant immediate early or conventional loading or placement, the peri-implant parameters, and the peri-implant health. There's another study. Who should place the implant? There was a retrospective study from 27 oral surgeons and 30 periodontalists. It was a training setting. All placed more than 100 implants between 2017 and 2019. And there were data from 54 clinics in Israel. About 27,000 implants were placed. And again, was not surprising, the more implants were placed, the lower the failure rate. There's a learning curve in the beginning. And what also was shown, the early failure rate was a little bit higher in oral surgeons than in the periodontists. However, there was nothing about the indications. Were all placed in the same indications or not? And this, again, did not learn us anything about the implant type or brand, immediate, early, or conventional placement or loading, the peri-implant parameters, and the peri-implant health, etc., etc. Then the studies, what was done in human subjects. First, a retrospective study was performed in 2009 and 2017. It was performed in the elderly patients. In 2009, 170,000 patients were involved, and in 2017, 260,000. And they were characterized like a natural dentition, in conventional denture, or an implant retained overdenture. Then the medical status of all those patients was recorded, medication use, and the socio-economic status. And they are all categorized according to the dental insurance declarations. Fact is, it's a very huge database in the Netherlands in which all what is done in the patient are recorded. And what is shown that elderly with a conventional denture or an implant retained overdenture had more often a low socio-economic class, and the patients with a conventional denture had a higher prevalence of cardiac disease, hypertension and diabetes than patients with a natural dentition or an implant retained overdenture. And because of that high prevalence, the polypharmacy was also most prevalent in the patients with a conventional denture. And it was the same at 2007 and at 2017. But it was also, again, a nice attempt, but no data on implant type, brand, placement, loading, health, and survival. Then the same group did a prospective study from 2009 to 2016. They followed, again, elderly patients, and each year from the insurance database factors, the following data were collected: the visit to the medical professionals, admission to a nursing home, the healthcare costs, the type of medication received, the total number of drugs received, and the medical conditions. There were data from 170,000 elderly. About 80% had a natural dentition, 14% a conventional denture, and 4% had an implant retained overdenture. Again, what was before was showed that the elderly with a natural dentition had a higher social economic status than the identity subjects. But what was very important, that the general health cost did not differ between the groups. But the subjects with a natural dentition had, of course, a higher dental care use. But also important to know that the nursing home admittance was the highest for the elderly with a conventional denture. And here we see the data, and what was remarkable that the patients who got an implant retained overdenture was in general had a better health than the patient with a conventional denture. And later on, the general health resembled that from the patient with a complete denture. So it looks a little bit that placing the implants was done in patients with a better health at the beginning, and the people with a conventional denture who needed an implant and the health was a little bit worse, that the patients were the dentists were a bit reluctant to place implants. And this is just the dental cost, or the dental use was much higher in the natural dentition than in the implant retained overdenture, and that was higher again than patients with a conventional denture. That was again a nice attempt, but no data on the implant type, brand, placement, loading, placement, health, etc., and survival. Then the oral health problems. They studied it cross-sectional. 1,325 against elderly people, community living elderly, and there was questionnaires sent about the nutritional status, the oral health problems, the health-related quality of life, frailty, activities of daily living, and the complexity of care needs. About 50% were edentless, about 40% had remaining teeth, and about 10% had an implant retained overdenture in this group. And then the elderly with complex care needs were more often had a worse feeding status than the frail and robust elderly. And the same patient had more often problems with chewing and speech. But what was surprising, that there was no association between the malnutrition, the oral health problems, and whether the patient was edentless or had a natural dentition. What you could see here, the malnourished people had more often widow, single, or divorced, had a lower education level, but the risk profile, the complex patients were more often in the malnourished people, while the robust people had mostly a better feeding status. But at the same time, it was no relation at all with the oral health. Remaining teeth, edentulous, implant support denture were equal in both groups, while the frailty, the complex care needs, the activities of daily living, and the health quality of life was much worse in those patients. So the health-related quality of life was significantly associated with malnutrition, while edentulous and oral health problems were not. So, again a nice attempt, but no data on implants other than implants were used for an implant-supported overdenture. Then the last study was a cross-sectional study performed in 2017-2018, again in the 70 years old people. It was the Embrace program, Samen Out, that's aging together. And this is an integrated care service aimed to prolong the ability of other elders to age at home for as long as possible by providing optimal support. And again, the following data were assessed: demographics, general health, oral health problems, the chronic and frailty indicator, and the internet for the elderly self-assessment. About a little bit more than half of the patients returned the questionnaires. There's a pretty good response. The dry mouth and the oral pain were most reported. And the elderly with complex care needs reported more often oral pain, oral dryness, and swallowing and chewing problems, and insecure feeling. But what also was shown that most robust elderly can visit a dentist, while the patients having the most problems, they need help to visit the dentist. Or it might be that you have to come to the patient himself when he is really in pain and can't come. What you could see here, it was not related to the implant-retained overdenture, but the complex patients had more oral pain, chewing problems, swallowing problems, a dry mouth, and an insecure feeling. Again, a nice data attempt, but no data on the implant type and brand, placement and loading, the health and survival. This brings me to another subject, the Sjögren's syndrome. Sjögren's syndrome is a chronic progressive inflammatory and lymphoproliferative disease, an autoimmune disease, characterized by the mononuclear cell infiltration of the exocrine glands with dry eyes, a dry mouth and fatigue as common symptoms. And we had a group of 335 patients. About 1/5 of the patients had implants, and they were matched with healthy controls from other studies. And we recorded all those patients the peri-implant health and survival. And the patient symptoms, health-related quality of life, the oral functioning, and satisfaction were assessed using validated questionnaires. Oh, the wrong direction. The implant survival was pretty high, 97%, after 4 years. And they had also a pretty good peri-implant health. The marginal bone loss was very marginal, and the peri-implant prevalence was about 40% was compared to healthy controls. Only the peri-mucositis was a little bit high. There were a little bit more point bleedings around the implants. And the overall patient satisfaction was high. Why was this introduced? Because in Sjögren's syndrome, and that's something which you do in the implant to get big data, the medical data, all patients were well classified. And the data were also from the general practice, not from studies. And we collected already the implant placement, implant health, and implant survival data. But data were missing again with regard to the implant brand, type of substructure, and the loading protocol. So, in this very rare disease, Sjögren's disease, and you can see here, the patient can have a lot of different complaints. And in our field, there are extraglandular manifestations, and it's mainly the non-Hodgkin lymphoma and mostly mucosa-associated lymphoid tissue lymphoma of the Schliephake glands. But it's very important to use the classification criteria. Then you can really combine data sets from different people. Because all patients had a dry mouth, dry eyes, and problems with the fatigue. The complaints in about 90% of the patients have at least one of these complaints. But you're also well classified, so you can form a unique patient cohort. In all patients, there was a biopsy. In all patients, there was serum drawn. In all patients, the dryness of the eyes was done with either ocular staining score or the Schirmer test. In all patients, unstimulated whole saliva was collected. And when you have a sum score of more than 4, so you need a layer biopsy or the serum, then a patient is classified as Sjögren's patient. So there were established criteria, and they were used worldwide. And because of uniform data, the data sets could be combined. And this, you could see here, you can combine the data from all over the world. In 2019, there were already more than 11,000 patients in this study. And nowadays, already more than 15,000 patients. And you can get such huge data sets. All patients were analyzed in the data sets. And you can score a lot of things and always score it in the same way. And that was a reason of a lot of studies which could be done about the safety and efficacy or the characterization of the outcomes of the influence of AIDS, etc., etc. So many general trends are shown. You get a better insight into the pathogenesis of the Sjögren's disease, and the characteristics and signs of the underlying Sjögren's disease are discovered. So, what is important for implant dentistry, for big data? Then we should start with a uniform registration of all patient data, as well as a uniform registration of the basal implant data. And of course also a uniform registration of the follow-up data. That has to be worked out to make it available to all people. And you can also add what you would like. You can add the data on the immediate early or conventional placement, or on the immediate early or conventional loading, etc., etc. And when executed properly, a lot of general trends can be studied, and etiologic factors underlying these trends can be deducted, resulting in more targeted diagnostics and treatments. So, big data, I tell you, is the future, can be the future, but you need a proper data set from the beginning. We first have to make an outline how such a data set should be. And when it is available, we can get all general trends, but not for an individual patient. That's a limitation of big data. I thank you for your attention.
Thank you very much for that insightful lecture. Please take a seat, and we will raise a couple of questions that came to our minds while we were sitting there. And Gerrit, did you receive any questions from the audience? We don't have anything here.
Yes, I'm sending them over to you. There's several interesting questions that you could take for all three speakers. So let's have a fruitful discussion.
Okay. So we start with the first one. What are the limitations of CAIS or RAIS? That probably goes to you.
Please, can you repeat it?
What are the limitations of
We can even show it to you.
clinical assisted implant surgery and and robot-assisted implant surgery.
Computer-assisted implant surgery or robotic-assisted implant surgery. So these are official abbreviations we found in the literature. Obviously, it is a broad term. Computer-assisted implant surgery is all or nothing. It's like AI, and Andreas can say, okay, there are several subdivisions of AI, machine learning, deep learning, and this is only the very superficial word. So in terms of computer-assisted implant surgery, as maybe we meant as static guided implant surgery, you plan in advance, and then you're not able to modify during your surgery. This is a limitation. And of course, as I highlighted, you need a three-dimensional treatment planning in advance. So you have to start with a cone beam CT. Higher radiation exposure. This is something you have to discuss maybe with your patient.
So let us. Meanwhile, we're proceeding with the next questions. I do have a question for two other speakers. How do we certify the quality of the data? Professor Dengel, maybe, because you said the prerequisite is to have good data. And then I would pass the same question to Professor Arjan, like how do we ensure that we have, let's say, homogeneous data or that data from health registries are collected in unanimous way, and how do we ensure to have the quality of data?
Yeah, thank you. It's a really good question, since data as it is labeled is usually coming from subjects, and they have their own background, their own expertise, etc. But in general, it's quite hard to do so, but there are some recent new techniques which allow a AI system, even a deep network, to visualize decision-making and to also highlight the data which is responsible for the decision-making. And based on that, you can better identify aspects which are outliers or which are abnormal in a certain way. And this could help you to balance the data in a certain way, which is, of course, important. So if you, on the other hand, would start a new setup, you can try to have many subjects at the same time. You should think about a balanced sample of different cases. This is another precondition which is helpful.
Okay, well, there are a couple of comments more than questions. Can you take an AI robot to court after it has placed the implant into the mandibular nerve? I guess not. It will always be the human behind it who is responsible for doing what is happening. And what real benefit do you see that goes to those who place implants in a robot placing the implant versus a fully guided AI-driven surgery by a human? Once an accurate planning is done, placing an implant is not so difficult. That's
yes, of course. So always start with the easy cases, let's say, the straightforward ones, and that I presented the case series that I found to the haptic navigation with a robotic assistance. Yeah. So this is the fully edentulous cases, and then it's more complex, and there we saw the minimum maximum deviation, and I told it was 4 millimeters, and I was quite shocked as I saw this, because with a, let's say, Danny Busa always mentioned brain-guided freehand surgery. I guess with a little bit of training, we can reach maybe 1 millimeter or less. So therefore, we have to be careful applying this in advance.
And I think this question relates to the basic data set. Can we, how can AI interact with big data? Can we make exact risk profile per patient, for example? I mean, we've seen that you have presented data that were incomplete in many dimensions. And coming up with a complete data set will probably create an administrative monster that is completely unusable for day-to-day clinic. What do you think about that? Is that a perspective at all, so that we come up with a data set that allows us to really draw valid conclusions on these healthcare background that you have shown very nicely?
From these data, it's rather hard. The general data from insurance companies and other things. Then we first have to develop a data set. What should be baseline? What should be follow-up? And then you can give a proper results, and not before. You can just some general trends.
Yeah. And Andreas, with your
well, I can add something. It's not only the data. Since we have the big advantage in this field that we are dealing with images, and images are manifold. And in the last 10 years, we have a real evolution of image-based topologies which could be applied for various tasks in images based on AI. So the best thing beside the data is to have a sandbox. So that's what we established, of about 40 to 60 different topologies which you can immediately test if you have the basic infrastructure. But then you can see how far you can come, even with a smaller subset of data, because you have these transfer learning opportunities, which could be adapted with some of the topologies very well.
Well, that relates a lot to image analysis, but combining these healthcare data in general, that seems to be very well viable. Yes, very viable to incomplete data sets leading to wrong conclusions by ignoring details.
Yeah, absolutely. This is now a major trend to use multimodal networks, which beside images use different dimensions. This is temporal data, this is spatial data, but also all the metadata, which is coming from the patients themselves, including the treatment before. So there are some data collection, at least I know from Japan, that there is a central database which is collecting all the clinical data of all patients, including the length of stay, the period of stay in the hospital, and the medication, and all these aspects. And this is step by step coming.
Yeah, there was one question related to that. The high-risk patients in the Chinese study that you presented would not be eligible to receive an implant. Would it become another way to personalize the contraindications?
Absolutely. And I think this is a new topic we have to face with. If we have such an AI predictive modeling, can we cover the consequences in the future? So if we have a negative outcome and then we tell it to the patient, and then it depends on the payer system. If the payer is the patient, him or herself, and then we can discuss it, and he or she takes the risk. But if we have an insurance-driven system, and then maybe in the future there will be a demand by this insurance system that say, okay, if you want to have an implant, let's go for this AI predictive modeling, and then if it's negative, you're not allowed to get some funding. Yeah. And I think there are totally new ways in the future, not only AI as a supplementary tool for digital therapy or applications, also what bring it up in the future for this predictive modeling.
There's a provocative statement. Should we get rid of our old school, highly complex classification systems and move towards a more continuous approach to diagnose disease and provide a maximum of personalized therapy by using unsupervised AI learning and big data sets like biobanks?
I didn't get the message,
sorry. Sorry, maybe you can, yeah, it's difficult to...
Sorry.
So it's all about, should we not get away from our more static classification systems, but moving towards a dynamic advice from AI and huge biobanks or data banks? What is your opinion on that? I mean, looking at the variety of the data that we may generate.
So what we learn from the field of genomics and proteomics is that our body is very much complex. And to really drop it down to a very individual treatment might be possible in some domains, but every mouth is different, yeah, so, and the biology behind the mouse as well. So I'm not so optimistic that this would work in a certain way. Of course, there might be a way to cluster people into different categories based on their age, their background, their nutrition, etc., and then start some of the treatments in a certain way.
So it should be an advice.
Yeah, yeah, right.
And not that you should do it. And when you don't do it, you have to tell why you don't do it.
Final word on data security. I mean, European health data space is coming up maybe in 2025, where everything should be collected and everything should be transparent and every patient should have access to his own data. How valid is this approach that we collect everything about everybody, and if someone says, no, I'm not going to give my data because they're mine, I'm not going to submit them into this huge data set, how do we handle that?
Difficult question. Yeah. So in general, I think we all agree if we would have the data from all the people available, we could have deep insights into the correlationships, dependencies, etc. But of course, I understand that maybe some people are hesitating into that. But I think step by step, the new generation is much more open to provide the data. I think it's a generation problem to have a certain attitude. And at the end, of course, if you are the master of your data and you decide for what period of time, for which purpose, what dimensions of data I would open up, yeah, and this might be a reasonable approach, so to help dealing with health in a better way.
I think maybe it's a generation, but also the region. In Asia, it's a different kind where we work with data, or in South America compared to Europe or the US.
But maybe also legal experts could be involved in terms of facilitating
They were highly associated with that. Yeah.
Exactly.
But the easiest is just to build the data sets and then go to the individual clinics and to the treating to see what for a particular patient is, and the others.
The attractive idea, I think, is if you have these huge data registries, like healthcare insurances, they collect all these data. And if you would have access to it, we don't need to deal with ethical committees for randomized controlled trials. We could just look at the data and what is there. But then the problem comes up, how complete are they?
Yeah. The challenge is not, I wouldn't say Asia. I think it's very much depending on the value system. And in some of the Asian countries, of course, they are more liberal or more open in a certain way, not liberal in our sense, but liberal to the data use. And this might be a big danger with respect to competitive aspects, so that based on what is collected and how it is used, and also the speed how it is used, might cause problems to European manufacturers of AI-based devices, that they will fail and the market will be just captured by Chinese.
Yeah. Well, 3 seconds left. Time to wrap up. We had an excellent session. I learned a lot, and I think it seems that AI and big data combined in the procedures in dentistry are probably closest to practical application. But identification of risk profiles from metadata sets remains still a little shaky. And I think what you showed us, Andreas, how important it is that you tailor your learning sets exactly to what you want to know, what you need to know. That really was very enlightening. So thank you very much. Thank you, everybody, for being here and listening to the discussion and to these 3 excellent lectures. Thank you very much.
Thank you.